Good afternoon, everyone. My name is Tom Simchak. I'm ESA's Director of Research and Programs. Thank you for attending today's webinar titled Energy Storage 101, Survey of Storage Technologies. This webinar is being recorded and will be available on energystorage.org. Questions can be submitted at any time throughout the webinar via the chat box in your browser. Following the webinar, you'll receive a brief survey regarding today's topic and topics for future webinars. Your feedback will ensure that ESA continues to provide the highest value information to you and your organization. So we really value what you all think. We'd like to hear back from you. This definitely does contribute to our ongoing work, these webinars in the energy storage sector. All meetings and teleconferences of the Energy Storage Association are held in accordance with our Antitrust Guidelines. We ask that you abide by these guidelines during today's webinar. Full guidelines are available in the members area of the ESA website. If you're not yet an ESA member and would like more information, you can reach out to my colleague Richie O'Neill. Membership includes free access to webinars, not just like this, but we have a whole range of different topics, drilling into a lot more detail on a whole range of topics. We had some great ones recently on interconnection, state spotlight on what's going on in Hawaii. All these are available to members as well as other benefits too. So please reach out to Richie if you have any questions. Before we begin, I'd like to give you a brief update on upcoming ESA events. The ESA annual conference will be held in Phoenix, Arizona, April 16th to 18th. This is ESA's premier event and will bring together the energy storage community. It's a really great program we're pulling together, all about the expansion, inclusion, integration of energy storage. So we really hope you and your colleagues will be able to make it out for that event. For ESA members, our quarterly market update webinar is coming on March 6th. We'll hear from Wood Mackenzie experts on what's happened in the last quarter of 2018, as well as annual figures for 2018 as a whole. It's a really great resource for those tracking markets for storage, so definitely reach out about membership if you're keen to join those. And on March 13th, we'll tentatively be holding a webinar on end-of-life and recycling issues for energy storage systems. Keep an eye out for those announcements. Really great resources for you and your work. Today, we are hosting the inaugural webinar in our Storage 101 series. This series is designed to cover the basics of how energy storage, the technologies, applications, and other related issues, how those all work to introduce our audience to the sector and its potential. Many folks, when they think of energy storage, they imagine traditional lead-acid batteries or lithium ion batteries that folks are talking so much about. But really, it's a whole range of other technologies that are involved in the energy storage world, and a lot more too, to batteries and different technologies and advancements that are happening in the battery sector. There's batteries, mechanical storage, thermal storage. So what we're trying to get at in this webinar is to kind of provide an overview of these technologies, to target it at sector stakeholders and those new to energy storage industry. So we'll discuss some of the factors that developers or customers consider in storage technologies and some of the characteristics associated with each resource. And we'll be continuing this series throughout the year, so keep an eye out for other announcements on other topics in this series. Today we're joined by three experts from the Electric Power Research Institute, or EPRI. We have Ben Kahn, Program Manager for the Energy Storage Program, Aaron Minear, Technical Leader on the Energy Storage Program, and Dr. Brittany Westlake, Technical Leader also on the Energy Storage Program. During their presentations, you can ask questions via the chat box at any time, and the speakers will address clarifying questions as we go, but we'll also have a Q&A session at the end. So any questions you enter there, we'll have time to get to them all at the end of the presentations. And thank you for attending today's webinar. And with that, I will hand over to Ben. All yours, Ben.
All right. Thanks, Tom. Thanks to ESA for inviting us to give this inaugural webinar on energy storage technologies. Let me start first by making one announcement. If you do have questions during this presentation, I encourage you to put them in the chat box. We'll kind of screen those as we go through and try to answer them on the fly. If we don't get to them in the actual progress of doing the webinar, we'll swing back around and clear up any open items at the end. Okay, so just very briefly to introduce EPRI and the Energy Storage Program. So we are a nonprofit collaborative research organization that works for the public benefit. Our guiding vision is safe, reliable, affordable, environmentally responsible electricity. And my job is to manage the Energy Storage Research Program, which has the mission to advance the integration and use of safe, reliable, cost-effective, and environmentally responsible energy storage. We do that through 4 major thrusts. One is that we evaluate technologies, and we try to provide guidance toward the market and technical needs for different technologies. We build tools and methods for analyzing the value and grid impacts of energy storage technologies. We focus on the grid integration of demonstration systems and trying to develop best practices for energy storage deployment. So this particular webinar, we're going to be focused on energy storage technologies. I'm going to start with an introduction to energy storage kind of from the big picture. Then I'm going to hand it over to my colleague, Aaron Minir, who's going to talk about attributes. What is the difference between different energy storage technologies and why do these attributes matter? Then Brittany Westlake will be walking you through the different energy storage technologies and some of their key attributes. And I'll provide a short wrap-up and share some of the available resources that we can offer that are publicly available. So what is energy storage? Very simply, and this will be no news to many of you who are on this call, but energy storage is essentially a device that takes electricity in, stores it, and releases energy out back to the power grid. And in the middle of there will be some losses in various forms, typically in the form of heat. When we look at energy storage in a bit more expanded way, and what we'll cover a little bit on this call, is that there's not just the simple electricity in and electricity out. There's also other technologies that behave like energy storage, and some may take actually some input fuel as well as storing electricity, and some may also have heat out that can be used to offset electricity use, or in some cases electricity may come in and produce a fuel like hydrogen or natural gas when it comes out. So just want to expand the scope a little bit. Most of what we're hearing about is the simple electricity in and electricity out, but there are other kinds of hybrid resources that we'll touch on that are not that simple. And before we jump into all the technologies and all the attributes, I just want to provide a little bit on the very big picture for energy storage technology deployment. It's important to realize that energy storage, while new as a hot topic of discussion over the last 5 years, has actually existed for a long time on the grid in the form of pumped hydropower, which is another technology that we'll be touching on in this webinar. Globally, about 95% of all installed storage is pumped hydropower. That's about 183 gigawatts globally, according to last access of the DOE Energy Storage Database. About 3 gigawatts of electrochemical storage and about 3 gigawatts of thermal storage as well. However, battery storage is really growing fast right now, and it's often when people are talking about storage, what it is that they're talking about. Due to electrification of automotives and proliferation of portable electronics, lithium ion batteries have been invested in to a great degree, both in R&D and manufacturing. And as a result, the costs are dropping rapidly. And as a result of that, about 98% of all new of these advanced storage or non-pumped hydro storage projects are now lithium ion, and all others make up about the remaining 2%. And just a fun fact at the end of this, just to give a sense of scale, we've seen in the first 3 quarters of last year, according to the ESA Wood Mackenzie Energy Storage Monitor, we had about 165 megawatts of new lithium-ion battery storage. And in a single project, Duke Energy in the Carolinas is constructing a 200-megawatt upgrade to its Bad Creek pumped hydro plant by 2023. So single project, very large. However, pumped hydro, as we'll talk about more, is very location limited, and so in the U.S., a lot of the capability to build out pumped hydro has already been built out. So with that, I will close my intro, and I'll hand it over to Erin Minear, who is going to first ground you in the technical characteristics and attributes of energy storage. Erin?
Thanks, Ben. Hi, everyone. So just to get started, we'll talk about power, energy, and beer. So storage is an energy-limited resource, so it's important to talk about both power and energy ratings of the storage. And we put it in a beer analogy to help people understand the differences between and the relationship between it. So starting with the Cornelius keg, you would have 40 pints, which we could equate to, say, 40 kilowatt hours. And the flow rate would be, let me step back a second. The power rating, which we often measure in kilowatts, is the rate or flow of the energy at one time, and it's analogous to the keg's flow rate, so pints per hour. And energy is the ability or the capacity to do work, often measured in kilowatt hours, and is analogous to the keg size or pints. So going back to the different keg sizes, if you have a 40-pint keg that has a flow rate of 20 pints per hour, you would have 2 hours of beer. And a lot of times when we talk about storage, we either talk about power and energy, but also it's referred to in the context of how many hours of storage you have. So we have power, energy, or we often talk about hours as well. So going to the pony keg, if you had 62 pints at a flow of 20 pints per hour, you would have 3.1 hours of beer. And then going to a full-size keg, you would have, at that same flow rate, you would have 6.2 hours of beer. However, if you were to change that flow rate or the power to 100 pints per hour, then you would have 1.24 hours of beer. And storage can be used for many applications. Some applications you would want higher power for shorter duration, while others you would want, maybe want longer duration storage for more hours. So this just helps to show the relationship between power and energy. And we'll see when Brittany talks about the different technologies, how some are more suited for shorter duration and some are more suited for longer duration. Next, I'll walk through some of the attributes of storage, and these can help to determine what is the best storage and for your particular use case or project-specific factors. The different technologies have different strengths and weaknesses, and you want to align it with the use case and the needs. So I'll talk about a few of the key ones here. Life is how long the system is needed, and it could range from a few years to decades. And also when you're thinking about life, you might want to think about replacement costs or overhaul costs, so what you need to do to extend the life of the system and how long you can extend the life of the system. The next attribute I'll talk about is footprint. So this may be important if you're in a rural area or an urban area, then footprint may be a concern. But if you're a rural area, maybe less of a concern. And there's also the footprint has a potential impact on the cost for how much site work needs to be done, or there may be other geographic considerations for project specific that are related to the footprint. Cost can be broken down into several different buckets. There's upfront installed cost, O&M cost, operations and maintenance, and decommissioning cost. And it's good to take a full picture of the cost because one technology might have a higher first cost but a lower total cost of ownership. Efficiency is another attribute. This can be important to the projects because there's a cost associated with charging. And it may matter more if you're charging and discharging frequently, such as shifting renewables, where you may be using the storage daily. But maybe it would be less important if you had infrequent use, such as backup power. Fast response is the ability to respond quickly. And again, this may or may not be important depending on your application. And lastly, modularity, how well the technology can scale with power and energy. There may be a minimum size that you can get with each technology for it to make financial sense. And there's also, you want to think about the incremental cost to add more energy or more hours of storage. We have an exhaustive list of technical specifications that's publicly available. It's called the ESA Technical Specification Template, and there's a link to the website where you can download that. And I'll go into a few of these in more detail. So starting with life, here we can break down life into cycle life and calendar life. So cycle life is the number of times the energy storage reservoir can be charged and discharged before degrading the system beyond the application requirement. The picture on the top right shows an example cycle life curve for lithium ion. And you can see here that the depth of discharge impacts the life expectancy. If you were to do deep cycles, which means that you're taking the battery from a full state of charge or a full battery and you're using all the energy within the reservoir, that would be considered a deep cycle, and then charging it back up. Cycling those deep discharges and charges would degrade the battery faster than what we call shallow cycles, which would be charging and discharging a little bit, but not using the full range of the battery. Calendar life is years until the storage system operates before degradation beyond the application requirement, so similar but measured in years, and that's independent of cycle life. Again, the picture on the right shows that for lithium ion, there's different factors that can degrade the calendar life faster. So the resting state of charge, or the temperature where the ambient temperature of the storage device. Other technologies, there may be other good metrics for life. You want to think about potentially overhauls or replacements of key components. So there's several different aspects to life that you should consider throughout when evaluating different technologies. Footprint is impacted by power density, which is the rated power per unit volume, energy density, which is the rated energy per unit volume, and also the packaging choice. So again, another lithium-ion example. You can see these three systems here, which were deployed in California with the Aliso Canyon battery storage installations a few years ago. These are all lithium-ion technologies, so similar in energy density, but the packaging is different and the layout is different. So the first photo on the left is a pre-engineered battery storage enclosure, and then the second one is within a building, so that one has a smaller, tighter footprint. And that battery system is part of a larger, it's installed in the existing gas plant facility, so they were able to use existing interconnection equipment, and so that footprint of the battery building, is the footprint listed there is just of the battery building, whereas the other one takes into all the other components that are needed to interconnect the system. So also when thinking about footprint, it's not just the battery, it's or the underlying technology, but all of the other equipment it takes to connect to the grid. And then the last one shows lithium-ion in ISO containers or storage containers. And so different layouts can impact the footprint of the technology. So it's a combination of the power density, energy density in packaging. Efficiency is another metric. So efficiency is the ratio of delivered charge energy to discharge energy to deliver charge energy, including parasitic loads. And when talking about efficiency, we want to highlight the importance of understanding exactly what's included in the measurement and how it's measured. You can measure, when folks talk about efficiency, it could be of the storage medium itself, or it could be the efficiency up to the point of interconnection. It may or may not include auxiliary losses, such as HVAC, electronics, pumps, or other mechanical equipment for some. And so talking about efficiency, it's good to get on the same page when we're comparing side by side of what the definition of efficiency is and what's included and excluded. The last thing I'll mention on here is the self-discharge rate. For some technologies, even if the storage is not being used, it could lose some of its energy over time while it's resting, so it could discharge over time. And if you're, depending on how your efficiency is calculated, if it's over a full day or a month, then that self-discharge could factor into the efficiency equation. Response time and ramp rate. Here I just want to highlight that there are differences in the response time between mechanically coupled and inverter-based storage. And again, for some applications with the need for dynamic grid services like frequency regulation, inverter-based storage could be a good alternative if you need that fast response. And lastly, I'll talk about safety. I didn't include it in that initial kind of web of attributes. One of the reasons is because even though there's inherent risks with each of the technologies, it's the integration and the protection that's key to ensuring safe operations. So there's different types of hazards, chemical, fire, stranded energy, electrical, physical, but these can be addressed with the integration and protection. Also, to help address some of these types of hazards, there's emerging standards, codes and standards, but the technology, especially advanced storage technologies, are moving a lot faster than standard development. So it's a really critical piece to evaluate and understand the different safety aspects and how the system is being integrated while the codes and standards catch up to the current technology advancements. Those are the key attributes, and I don't see any questions in the feed right now, so I'll hand it over to my colleague, Dr. Brittany Westlake, to talk about the different storage technologies.
Thank you, Erin. And I hope everyone in the audience, kind of feels like they have the beginning of an understanding of how some of these storage technologies work. The good news or the bad news is next, I'm a physical chemist. So I'm going to talk to you about, some of the mechanics or the chemistry behind some of these works. And hopefully I haven't lost you already. If anyone hated chemistry, it'll hopefully give you an understanding of how this energy is stored. Essentially, energy storage is just storing potential energy on the grid. We talk about how there hasn't traditionally been a lot of storage on the grid, but as a chemist, I would argue we've had that stored energy in the form of coal bonds, in the form of natural gas bonds, even in your car, your gas tank with gasoline. All of that energy is stored in those chemical bonds. And so I look at energy storage sometimes as a way that we can store that potential energy at a time when it's convenient and then recover it later. And there's lots of categories. So thinking through, what are the different ways of storing that energy? There's, of course, electrochemical batteries, a number of different types of those, electromechanical storage, and we'll talk closely on compressed air energy storage, the pumped hydro that Erin mentioned, flywheels. And I'm not covering it in this talk, but there's a lot of research and focus on emerging storage in the electromechanical. There's a technology that takes, blocks or train cars with rocks, moves them uphill, and stores them, essentially with the gravitational potential energy and can be recovered later. There's other companies that look at, electric motors that can store and stack blocks the same way a crane building a building would do. but then adding the regenerative aspect of dropping those blocks later when you want to recover that energy. There's also chemical storage. So using electrolyzers to split water and produce hydrogen and storing that energy in a hydrogen bond. There's electrical storage where you have capacitors and you're storing the charge on a surface. There's superconducting magnetic storage. And there's also thermal storage, looking at storing the thermal energy from, say, a natural gas plant or a coal plant or even a nuclear plant, as well as a solar installation, and storing that thermal energy, in a chemical material or different ways, and then recovering it later. And we're seeing a lot of new technology advances in the thermal area, at least as well. I'm going to go into more detail on more traditional, but just know that kind of the same way you think about how batteries can store potential energy, there's a lot of emerging technologies that are interesting to research. One thing that's challenging on it from a technology scouting perspective is, talking to a number of these people developing. I'll talk to someone one day whose, pilot demonstration project is the size of a toaster, and then I'll talk to somebody the next day whose pilot demonstration project is the size of an elephant. So, kind of thinking through Aaron's discussion points on the footprint, sort of the underlining characteristics of these storage technologies, just because they are so broad, can vary widely. But I would challenge everyone to think of them as kind of strengths and weaknesses on a technology, or maybe not even weaknesses, just sort of the technical characteristics that storage solution is best suited to store energy. I think looking across the electric power grid, there's a number of areas across the grid where energy storage can be a really useful technology. And so one of the challenges, I think, is thinking about all these storage technologies on where their strengths are, where their technical capabilities are, and thinking about then how we map them to the grid challenges. So going on this slide, this is, in addition to Aaron's spider chart where you think about life, efficiency, cost, fast response. This is a simpler two-dimensional way of looking at just even the sizing of the systems, the practical sizing from kilowatts up to gigawatts, and then the discharge duration. Kind of mapping out and thinking, depending on the grid challenge or application, what size system might be best suited. And also going into some of the modularity. Thinking about pump storage hydro, you probably get some of your benefits from doing larger systems of scale, but you could also do certainly a smaller pump storage hydro system and just looking at the economics and where it makes the most sense. So now jumping into the technologies, the first one I'm going to talk about is pumped hydroelectric storage, and I think it, in addition to be the longest used one on the grid, I think it's a good example of kind of that potential energy. It helps me to envision, you're pumping the water uphill, you've got that gravitational energy stored in that water up in the reservoir, and the system is designed then to let it flow downhill back through the pumps where it generates electricity in just that section, like similar to a regular hydropower plant. In talking about footprint, obviously you're looking at bigger spaces for this water, the water reservoirs than you might for a battery system, but you're also getting benefit of scale. Once you build the infrastructure to pump the water and then recover the electricity, additional energy, or in Aaron's analogy, making the keg bigger is just expanding that reservoir on the top and the bottom of the system. The typical efficiency of pumped hydroelectric storage is in the 75 to 85% range. And thinking about life, maintenance on the pumps, one of these things is, we talk about self-discharge in battery systems. In this case, one of the self-discharge issues you'd have to think about is the water in your reservoirs evaporating. So kind of in all the basic parameters that we're trying to give you for the different storage technologies, think about how these technologies are very different and they might look differently as you apply them to different technologies. The next technology I'll cover is lithium ion batteries. And I'm sure, you're on this webcast. I'm sure you haven't missed any of the news on the large deployment of lithium-ion batteries. They work in a similar way of storing the potential energy within the battery, but in this case, it's lithium ions that get shuttled from the anode to the cathode across the battery, and then are able to be recovered when you discharge. These technologies have advanced dramatically in the last 10 or 20 years, and they've also benefited from manufacturing scale with electric vehicles. So we're seeing a range of chemistries and different sort of flavors of lithium-ion batteries that are starting to be very cost competitive on stationary markets, whether they're residential or larger transmission-connected systems, to provide flexibility on the grid. Cycle life for lithium-ion batteries is usually 3,000 to 10,000 cycles. So depending on how much they're used, as Aaron covered on the life of the systems, whether you're doing full discharges, that's going to shorten your life versus shorter discharges. And also thinking about system design. The thickness of the cathodes and the anodes can be changed to increase power versus energy, but you also have to think about kind of the balance of plant systems. The inverters, the other aspects of the lithium storage system, and how that affects, the power capabilities of the system. The same way, I guess, you would change the tap out on your beer keg, to get a higher power flow or a lower power flow. And that is definitely doable in any of the cases designing systems, but it also affects the efficiency. So like anything else, there's trade-offs in designing a system, and it's, best to have one that's sort of maximized for your application. So you can take advantage of its, strengths and characteristics without, and minimize the trade-offs on any technology. Another historically deployed energy storage is compressed air energy storage. And one of my colleagues here at EPRI was integral in installing the Alabama case plant. And compressed air energy storage, it uses pumping air into underground cavities and then creating the pressurized potential energy of the air in those cavities. And then the air is allowed to flow back up, and they recover that energy by combining it in a gas turbine and increasing the efficiency. So that is another technology that has been deployed in 2 instances. Like pumped storage hydro, it can be geologically limited, but there are a lot of research going into sort of decoupling some of compressed energy storage in adiabatic or other cases so that it's not as tied to geologic limitations. Another technology that's sort of interesting to think about from an energy storage perspective is flywheels. So currently on the grid, a lot of our generation is based on coal, nuclear, natural gas, and all of those are, any steam or thermal generation. The power is generated by rotating machinery to create the 3 phases of electricity that we have on our grid. And as we think about new and alternative technologies, or even, locational areas where we don't have that frequency response on the grid, flywheels can play an important role to store some of that rotational inertia and help balance kind of the power on that side. Not going to get into the physics of volt and var, but I will recommend MIT's Future of the Grid. At the very end, there's really good appendices that kind of go into the physics of balancing the 3 phases of the electricity that I think at least looking through the pictures is accessible even if you're not a physicist or a chemist. And there's several companies and technologies developing different flywheel technologies. Another traditionally established battery technology is the lead-acid battery. They are widely used for telecommunications backups, buildings backups. I challenge the group now. I play a game when I walk around airports and other facilities that have backup power needs and I often come across a room that will say battery room. And a lot of those are backed up by lead-acid batteries. They have some challenges in their lifetime, and often they have maintenance. If they're filled batteries, they need to be kind of monitored and then refilled with water. But one area that the lead-acid battery industry has really excelled in, especially here in the United States, is their recycling. They are 98% recycled here in the United States. So while they are an older technology with some environmental challenges, I think the industry as a whole has really made the effort to step up and think about how do they collect, reuse, and recycle these materials so that they can continue in a sustainable process. And then another large battery technology, well, I guess it also has the option for modularity, is flow batteries. And we're seeing many different chemistries being developed, and sort of in a traditional battery with lithium or lead acid, where you have a cathode and an anode separated physically with an electrolyte that allows the ions to pass back and forth as the electrons are either charging or discharging from the battery. In a flow battery, you have just that, two liquids that are able to flow through the system, and they're stored in tanks, so you're separating that potential energy of the system when you separate the electrolytes in two different tanks. And then you can charge the battery by flowing them through a stack, and then you can discharge the battery by flowing those two kind of potentially energy separated electrolytes back through the stack cell to produce the electricity. Now we're seeing a number of chemistries and a number of technologies developed in this case. One strength that flow batteries have over traditional lithium-ion and lead-acid batteries is the ability to decouple the energy and the power. Whereas to increase the power of a flow battery, you simply increase the stack size and increase the energy of the system, you can increase your electrolyte tanks. However, we're also seeing some modularity in flow battery systems, where in manufacturing and ease of installation, they're coupling the power and the energy to create kind of a modular system that they can install and just add multiples of those. So it'll be interesting to watch as this technology continues to develop. Another technology that we're seeing is thermal energy storage. And that is kind of manifesting in multiple ways on the grid. Some is in ice storage, where you're using air conditioning to do the phase change between liquid water and solid ice, which is an excellent way to store energy and then recover it later. It's not strictly electricity in and electricity out storage, but it is kind of a novel way to shift the electricity use on the grid. We're seeing others where you would collect solar energy, store it in a thermal reservoir, and recover that thermal heat afterwards, like you see if you've done the cross-country flight. Sometimes from my airplane window I can see the solar collectors with the tower out from the plane. We're also seeing thermal energy storage where electrical energy is used to create heat, and that heat can be stored in a number of mediums, sand, concrete blocks, thermal bricks, in addition to kind of molten salts, and then that heat can be recovered later to optimize thermal processes on generation plants or even back to electricity. So that is another technology area that we're watching. And so it looks like we got some questions in. I apologize, in the interest of time I went quickly on that, but now I will review some of those questions, unless Ben would advise me to wait to the end.
I think we can, I only have a couple wrap-up slides. Why don't I go ahead and finish up the presentation? And then I see that there's a number of good questions in there, so why don't we come back to those in a few minutes.
Okay.
All right. So I just wanted to end with this note that when you choose the technologies and design projects, it's not just the attributes that have been talked about here. There's really no single answer to technology selection or project design, how big the system should be. Value cost and the risks associated with the project all really need to be considered in parallel in the design phase, and that includes really understanding your application, what you're trying to solve primarily, what is the motivation for putting storage in, and then if there are other opportunities to make value above and beyond, or create value above and beyond that, there is a lot of talk right now about multiple use applications or stacked benefits. And even if you start with just a single service in mind, there's the potential that over the course of the life of that storage plant that it could be extended to address new services and create new value streams as the conditions on the grid change or other factors. Also, siting is really important. So some of these technologies are very locational specific. If you think about pumped hydro, you need the topography, the geology to do that correctly. Same with compressed air underground. In other cases, with batteries, for example, they can be put in many different places. They're not tied to a particular set of site requirements. Also, it's important to consider with risks and with safety, where you want to have, what you want to have near these systems. Certain technologies may be better put in remote areas where if there was a safety issue that it was far away from property or humans. In other cases, the technology is may be much safer and able to go closer to homes and buildings. And then finally, the vendors and the integrators can take on some risk as well. It shouldn't always be solely the buyer that needs to worry about these things. So to some extent, the companies that develop these technologies should be able to express what risks are inherent, provide guidance on how their technologies have been used, and also offer contracts such as warranties or performance guarantees to help mitigate any of those technology risks. A couple of resources I wanted to highlight. So as it pertains to finding projects, we do offer a publicly available valuation software to support project-specific valuation. This is this tool, the Storage Value Estimation Tool, or StorageVet, has been developed over several years thanks to the support of membership of EPRI as well as the California Energy Commission. This is a publicly available tool that's available online at storagevet.com. Also, we are in the process of overhauling this tool and making it an open source tool based in Python, so you'll be able to take that tool and extend it to your purposes if you're developing storage systems or comparing storage systems. There'll be a lot of potential with the next phase of this open source tool. Other resources, we have a number of other resources that can help with specification, understanding cost, modeling and safety of energy storage. This is through an open forum that we call the Energy Storage Integration Council. It's been around for about 5 years, and there's something like 2,000 technical collaborators working together to develop a series of publicly available guidelines and tools, which you can find at www.epri.com/ESIC. And if you're interested in participating in this activity, esic@epri.com is our main portal to request to join this group. And our next meeting will actually be the day preceding the next ESA annual conference. So Arizona Public Service will be hosting us there. And this is our contact information, myself, Ben Cowan, as well as Aaron and Brittany, who you just heard from. At this point, I think is a good time for us to go back to the questions. So Tom, would you like to take us through what you've heard? I see there's some questions lighting up there.
Yeah, definitely. I guess we'll kind of start out with some of the more quick and practical ones. We'll have to move through these a little bit quickly as we do have a lot of questions, not a great deal of time. We have a question from Deanna Dennis. Hello, Deanna. Good to hear from you. Which technology is better for load following capabilities versus longer, more stable duration discharges? And then also, what is EPRI doing in terms of valuation and integration of storage technologies?
Well, I'll pass on the second one because I think I covered that a bit, or maybe I'll say in addition to the tools that I just laid out, we're also interested in being party to demonstrations and to collect data on performance and reliability of systems. We're working toward developing an industry database there because it really is nascent industry right now in terms of commercial systems. It's only been a few years for a lot of these technologies that they've been out in the field, so we really need to improve our data sets and understand the real reliability issues in the field. The question about load following versus, or what I'll call it, steady state operation versus load following. So interesting thing about that is that most storage technologies really don't have much trouble with flexibility like some conventional generators do. Some are very fast at following load like batteries. We're talking millisecond level response times. And some are a little slower like pumped hydro and compressed air because they contain mechanical systems. However, as it pertains to battery technologies, following load is not really an issue. That's an issue for thermal systems, not so much with energy storage systems.
Great, thanks so much. Quick question, please define state of charge and mileage ratio.
Sure. So state of charge, sorry, this is one of the things that was left undefined in the slides, but a state of charge refers to basically if you've got your keg of beer, how full your keg remains halfway through your party. So half full is 50% state of charge. And then I'm sorry, what was the other question again?
Mileage ratio.
Oh, mileage ratio. So mileage is kind of a wonky term that is used primarily in discussions about frequency regulation. It has to do with the up and down travel of a storage system to follow a frequency regulation signal. So that's been described kind of tangibly by others as, imagine you have an up and down charging and discharging signal that you're following with your storage system. And if you were to take that signal and turn it into a string and then pull that string tight, that's your mileage. It's essentially how much it's traveled. As I mentioned in the last question, it's not such a big issue for energy storage systems, but it is a fairly big issue for thermal systems.
Great, thanks.
Ben, if I could just build on your state of charge, kind of from a physical thinking about the system, from pump storage hydro, you can think about state of charge as if your top reservoir is fully full, then you're at 100% state of charge. You can, in theory, discharge all of the water in that reservoir, versus if your top reservoir was empty and your bottom one is full, you're at 0% state of charge, and in that case, you have a grid asset that could absorb all that energy and store it for later. And there's a similar, analogy of thinking of lithium ions on, the cathode versus the anode side of a battery. Those lithium ions actually physically move across the cell. And so thinking, if 70% of them are in the charge state and 30% of them are discharged, that's what you're thinking about in your state of charge, where that battery is in terms of the potential energy stored across the system, if that helps, people who are envisioning that in their head.
Thanks so much. Question from Derek Webster. Can you briefly discuss environmental factors pertaining to different battery types or different storage types as utilities try to reduce environmental impact? What are some of the considerations there? You mentioned a little bit on pump storage, but perhaps some of the others? Or let us.
Yeah. So I'm going to frame it a little bit. It's a simple question that can get kind of detailed and complicated quickly. So really what we're talking about is life cycle analysis for different energy storage technologies. And in the life cycle of these systems, there's basically everything it takes to make the product. Then there's the operational phase, and then there's the end of life phase. So you really need to think about all three of those. So making the product or the device, obviously if you're making different battery systems, there's going to be different, mining and manufacturing processes that go into that, transportation to get things from point A to point B. And then in the operational phase, it really depends dramatically on the usage of that device and the characteristics of the grid that you're operating in. For example, if you put storage on a grid where you have really high renewables penetration versus if you have one that's primarily fossil generation, there's going to be different greenhouse gas impacts. And then based on how you use that system, there's going to be dramatically different greenhouse gas impacts as well. And then at end of life, you're talking about things like disposal and recycling, and the recyclability of different technologies. For example, lead acid batteries are very highly recycled currently. Something like 98% of lead acid batteries go into new lead acid batteries. The lithium ion batteries, it's not nearly as closed loop at this point in time. There are some big efforts underway to try to close that gap. DOE just announced a $15 million initiative to build a recycling center of excellence for lithium ion batteries. So it's a known issue that is being worked on by the industry right now. So I know I kind of obliquely touched on the question. I don't have an easy answer for it. It's probably a good subject for a future webinar where that can be unpacked in a more dutiful manner.
I can then, of course, take the opportunity to flag our upcoming webinar on end-of-life and recycling issues, which will at least get at the question of what happens to equipment, batteries, etc., when the project is done.
There you
go. Combined two questions here to keep things moving along. What technology is best for long-hour operation, like backup or resiliency? And what resources can you recommend for regarding battery degradation?
Goodness. Let's see. Brittany or Aaron, you want to take that?
Backup power and resiliency in terms of a long discharge, I think in one case you definitely want an energy technology. And so, you can do that with a number of technologies, and in that case you just need to build them big enough that they have the energy reservoir to discharge their power over a long time. So you could do that with, I guess some of it depends on the siting locations. Are you doing this for a town? Are you doing this for a house, for a small surgery center? The other thing that we're seeing in energy storage, because it is storing energy, it's not creating. If you're looking at, resiliency over a long term, so say, an outpost or an island where you might have a potential for a hurricane and the grid to be down for 2 or 3 days. If you look at coupling your battery storage with, or your storage with solar, then you need a big enough battery to store that solar and discharge when the sun's not shining, and you can operate off. And that, so it's kind of from a resiliency perspective, a trade-off between how long, what are your core kind of key equipment, and can you couple it with anything else to kind of recharge it along the way to stretch out that resiliency time period. I don't know if that answered the question.
Well, thank you.
The second one was on degradation.
Degradation, yeah. So I can't direct to any specific resources, but just to touch on the idea of battery degradation and the challenges with it, and when modeling, some of the challenges are often you get cell level data when you really need system level data to understand how the system's going to behave. And the data may be extrapolated for some of the shallower depths of discharges, just because they can't run it that many times. So those are some of the challenges, and EPRI is currently doing some research to better understand battery degradation and state of health and actual operations. So right now, in our modeling, a lot of times we will try and get the data specifically from the manufacturers. So I can't point to any specific resources, but just to highlight, when you are doing those discussions, what type of data are you getting? Are you getting the system level data? And I think that as we deploy more and more storage and have more experience with it, we'll have a better sense of degradation and the state of health of the systems over time and with different applications and all of the factors that affect it, like environmental conditions and the use.
Right. Thanks so much.
And building on that, the storage vet software does have kind of degradation involved. And I think to Erin's point is some of this, as the industry matures and we see more, operation and maintenance schedules, I think we'll as an industry be able to identify, when does this component fail? How often do you need to change the quote unquote oil in your battery? Similar to how you have a car maintenance schedule. I think as the industry matures, we'll be able to kind of develop some of those guidelines and have a better sense of how the system as a whole degrades and ages over time based on use.
Great. Thanks so much. Quick question. Can you define state of health with respect to battery storage?
State of health in some ways depends on how end-of-life conditions for that technology are being defined. For lithium batteries, which is commonly discussed in terms of state of health, the end-of-life condition is often considered to be a percentage of remaining energy that can be stored in the reservoir. So if it was a 1 kilowatt-hour reservoir to begin with, they may set the end-of-life condition at 70% of that, or 80%, depending on the technology. And then the state of health is really a measurement that is defined in the context of that technology. It's meant to be sort of an odometer on your way to that end-of-life condition. And at different states of health, you may have somewhat different, somewhat degraded performance, whether it's that energy that's able to be stored or the efficiency of conversion.
Right, thanks. Do you have information about specific development costs, so per kilowatt or kilowatt hours?
Yeah, we do actually, and that was we do have a publicly available resource on the cost of energy storage technologies. We do an update every year. Erin, would you be able to pull that number? I mean, maybe that's something we can broadcast via the chat so people can find that publication.
Yeah, I'll send the product ID number.
Okay, so what you can do is when Erin sends that out, if you go to EPRI.com and you search for that number, that'll come through the chat, then it'll take you to the Energy Storage Cost Study 2018 report.
Great, thanks. Let's see, one last question. You mentioned Duke upgrading the pumped hydro site. Do you have any thoughts on the future of pumped hydro? I mean, it's a bit of a traditional technology, but are there opportunities for retrofits or other advances going forward?
Yeah, some of my colleagues in EPRI's hydropower research program follow this in more depth. There are currently different plants that are being looked at. There's a few new plants being looked at across the United States. Typically, we call it a closed-loop pumped hydro that doesn't not a kind of run-of-river pumped hydro. But the permitting process can be challenging there, and so they do take some time. Some retrofits like Duke's are underway or about to be underway. I think Duke is the only one that I know of that's kind of active or going to happen. There's a few other utilities like TVA and I believe Xcel Energy that are looking in their plan at the potential for other pumped hydro plants. But typically the really good sites have been taken. There are abilities to retrofit, particularly on providing flexible pumping or adding some pumping back capabilities to the system. But they're very site-specific, of course.
Great. Thanks so much. Well, that brings us to the top of the hour. I'm really sorry to those whose questions we weren't able to get to. We had some questions related to some financing issues, which I think we might hold to our Energy Storage 101 webinar on financing, which will be coming later in the year. So do keep an eye out for that. Let's see. So before we conclude today's webinar, I'd like to remind everyone about ESA's annual conference in Phoenix in April. And like to once again extend a great big thank you to Ben, Aaron, and Brittany for joining us today. Super informative, covering a lot of territory there. Hopefully, folks really got a lot out of this. The recording of this webinar will be available. Participants should get an email about that in the coming days. We also hope folks can take a moment and offer feedback in the feedback box after the webinar. So with that, thank you very much to everyone. Please get in touch if you have ideas for future topics of these webinars or other work by ESA. I'm also happy to talk to you about membership if that's of any interest. So with that, I'll draw the webinar to a close. Thank you very much, and have a great afternoon. Goodbye.
Thank you, Tom. Thanks, everyone.
Thanks.